Good morning, everyone. Hopefully you're here to hear about data Dropboxes and data Gloveboxes. My name is Clay Benziger, and I work for Bloomberg. I work in our Hadoop infrastructure team. And I want to give you kind of a philosophy behind some techniques that we've been using and we've been finding very useful for data security. With that, if you're unfamiliar with who Bloomberg is and what we do, I want to give you a background on our company. This is our iconic product that most people know us from TV, but behind that comes, we actually started in 1981. We have over 325,000 subscribers, over 170,000 countries. And what we provide is provided by 19,000 employees. It's quite impressive. We have over 5,000 software engineers. We do a lot of technology. With that comes the data science world. We have over 100 machine learning scientists at this point. Similarly, all the data engineering that goes into that. And that data engineering, especially by some of our services, such as our news service, you may have seen Bloomberg TV, for example, has more reporters than the New York Times, the Washington Post, and the Chicago Tribune. We actually get more than 125,000 sources coming into us. We get more than 1.5 million stories per day. And it's also one of the largest private networks, or infrastructure even, generates a lot of data for us. With that, all of the financial data that our subscribers tend to be active on and paying most attention to generates over 100 billion what we call ticks a day. And so that's a peak of more than 10 million messages a second. Some other kind of fun stuff. We have our own email and instant Bloomberg chat system that people actually trade securities on. So if you ever thought, hey, yeah, I just lost an email, that really stinks. Well, especially if you're trading money with that or something else that you can lose money with. So with that, this is what we provide our customers, news and finance of the world. And what this talk centers on is something that shaped my life as a boy. I grew up near this. It's a nuclear materials manufacturing plant outside Boulder, Colorado in the USA. It was called the Rocky Flats plant. Here, plutonium was manufactured for atomic weapons. Definitely kind of a very scary thing of engineers before our generation, but we still deal with it. And how does that relate to us? So let's think of what engineers of that era had to use. They would have a Dropbox, effectively, somewhere they could put plutonium, people didn't get near it, and it was isolated from them. And that was a container where basically they could deposit something to be retrieved later. And we see a good example of that here on the left image. It's a very large robotic retriever of drums of plutonium. Now, people would actually have to do stuff with this material to make it into the final product. And this was before quite as much advanced robotics as we have today. So we see here on the right somebody interacting with a Glovebox, which was a sealed protective container in which they could safely manipulate this dangerous material. And when I say Glovebox, I don't mean something in your car. I mean exactly this. We see somebody using gloves. They've got a port that they're looking through to be able to actually see what they're doing. They've got a lead-lined or otherwise protective barrier that prevents the radiation from causing them damage. Well, how does that relate to us in data security and data science? Well, if we've got a data Dropbox, that's some system where we can put a file for later retrieval. We really want to be able to try to protect that data so that we maybe can't cause it harm. We want to be able to make sure that data didn't get corrupted. With plutonium, it's not going to change for a couple 100,000 years, tens of thousand years. But data, that can change on us. So we want to be able to verify it. Similarly, for the Glovebox, we want to be able to manipulate that data. We want to do our analytics on it. We want to do our processing, whatever our country allows or various rules and regulations allow. But we need to make sure that we don't accidentally release that, as numerous data breaches of people accidentally leaving data on laptops or USB sticks have shown. We really have to make sure we know where that data is going. So let's talk about one way that this was done for plutonium. They'd have kind of an enclave. We can see here three fellows working with full respirators, being able to actually machine and modify the material. But here the material's at rest. It's more than comfortable in its environment, and the people are really inconvenienced. And if anyone's ever worked as an infrastructure engineer dealing with data scientists, inconveniencing data scientists really doesn't work well. They'll usually win the argument, and they don't like this. So let's think of what a data enclave looks like to make sure we try to give them a better experience than that. So Cynthia Dwork gave us a great terminology of a curator model that is something to restrict access and operations and results. Basically, you have a curator, like a museum curator, who is always in the pipeline. And that could be potentially something that's always permanently there. You can think of this as Apache Ranger, perhaps providing your data masking and things like that. Or it could be something much more complex, such as maybe a process that does statistical disclosure control. It tries to fuzz your data. And, well, that's useful. But in business processes, that starts to get a little hard, because we're actually changing the data. And if we need to make a business decision on that, maybe how much to charge a customer, they don't usually like it if we say, probabilistically, you accessed about this much data, please pay us money. So that doesn't work for all use cases. Now, we can think of some very good features of data enclaves, as they're actually called in the social sciences. And a great example is the US Census data. It's something that has information about all US citizens while they're alive, and most people don't want that to be revealed, again, while they're alive. So social scientists can use that data, but they use it in a data enclave. And often it's a laptop with all of its USB ports sealed, no way for you to actually connect and bring in a digital device. You've got a notebook, and you can take notes. And somebody will read those notes on the way out of the room, and that's it. Again, most data scientists I know would probably quit if I asked them to do that. So that kind of prevents business automation, but it does allow two really great properties. We have direct and exact access to the data now. It's not statistically modified. And it allows for arbitrary computation. So let's think about how the plutonium engineers solve this. Nuclear engineers came up with this Glovebox, and here we see somebody using robotics. They still have protection so that they can't track the material home with them. The material itself is protected. Plutonium actually spontaneously combusts in oxygen, so you kind of have to do some interesting stuff with the atmosphere it's in. And here we've got all of that. So what does that look like if we're doing that for data? Well, that equivalent of the leaded pane of glass is perhaps, in many cases that we've found, a remote desktop system. Ideally, without any way to get the data out. It is your pane of glass. Yes, you could screen scrape it one image at a time, but you know you're doing something wrong pretty clearly if you're doing that. But you aren't going to accidentally download it to your corporate PC or your personal laptop and go, oh, I'll deal with that later. No, you're clearly using a system that's intentionally left there. Similarly, the glove ports. Well, we need some way to run arbitrary code. We want to be able to use code to manipulate our data. That is the point of our careers usually. And we need that robotics to be able to achieve that. So this is some workflow management, ideally a deployment process, as well as routine operations. The routine operations can be things like just ingesting the data and doing your trivial ETL. Deployment could be deployment of models and deployment of much more interesting things, and that gets kind of tricky. Now, in Glovebox technology for the nuclear processing industry, they had pass-throughs. Basically, you would start with an ingot of plutonium, and at the end, you would have some very classified thing that apparently blows up really badly. Firewalls are insufficient, though, when you have stuff that spontaneously combusts. So they would actually have to make very explicit ways to pass the material through the facility. In our case, firewalls, as we know them, in the IT sense, are not sufficient. They're layer 3 devices, layer 4 devices. They can't actually inspect the data going through. And they don't know if that data is code that's being downloaded from a server just fine or if that's actually somebody's personal data. We do have deep packet inspection. They can unroll certain types of protocols. You know, REST, for example, for HTTP is one that a lot of vendors will be able to do. But a lot of what we deal with is protobuf wrapped, or it's some custom protocol like Zookeeper. Similarly, databases are another way to do pass-through. Again, deep packet inspection likely won't be able to catch that and unroll it. So now we have to think of the firewalls that they actually had in the Glovebox to keep things from spontaneously combusting and what the equivalent is for us in the data world. And that, again, is making sure that we actually isolate users and workloads from each other. Just because we have a data scientist who can read data set A and a data scientist who can read data set B, both working on the same cluster, they probably shouldn't be able to read each other's data sets. So we have to think about all of the various file systems they have access to where data could accidentally mix. So this is the distributed file system, our HDFS perhaps, our S3, local file systems. The actual Linux box we're running on, it has a file system that perhaps people can write to regardless of who they are. And then the processing itself, network protocols, network servers coming up. Spark, for example, is actually just a bunch of network servers. If I can connect to your Spark processes, I can potentially download their data. So with that, what does this architecture look like? Here we have a Glovebox in the blue pane, and we have the rest of the world outside. Now, how do we actually kind of get all the communications to move through? We look for that we've got Git, where we actually develop code, something that the engineers or the scientists can write to, outside the Glovebox. We've got an external database. This might be your customer billing system. This might be some other system that has to interface with the outside world, but it's got its own protections your auditors say are perfectly fine. And then you have your insecure client, pretty much everything else. And what can we do to restrict it? Well, we can try to make sure that when we talk to something like a Git repository, it's only read-only. So again, our deep packet inspection firewalls could help make sure that we can only do Git requests on an HTTP system. Same thing for databases. We can secure those databases potentially. The client, again, that secure desktop provides us that Glovebox interface for the humans. And we've got to actually make sure that we can get data out potentially or in as necessary. And especially the in part is a really big one, it turns out. Getting data into a secure system is sometimes harder than getting it out. And so we need to make sure we have a write-only interface of some sort. And then within the cluster, we have to make sure that we actually have, here we have two different applications, one a Python application, and that might be our glove interaction, people actually manipulating data, versus a scheduled application, kind of our robotics equivalent, but that might be somebody doing a compaction on an HBase table or something. And in the middle, we have that HDFS, a potential mixing point. And we still have to have that firewall that prevents our users going through that somehow. So let's step back. Let's kind of think about the Hadoop architecture. And we're going to focus on HDFS for a moment here, and HBase and Yarn. And we can see here that we've got a mixture of, again, HTTP protocols and RESTful protobuf protocols that we can use. One of the key things here is to think about what are the security points. With Yarn, for example, we see that we can get logs out, but submitting something, getting a status is all relatively information-free. The app web UIs, however, are arbitrary. That could be, if you're a Spark user again, that could be your Spark application web UI telling you how much you've gone through your process, and arbitrary logs, which could, again, have data. That could be just an arbitrary Python notebook if you happen to deploy, say, a Zeppelin notebook to your Yarn cluster. So this is a kind of a security concern. With HBase, we've got get, put, and scan. Well, certainly puts aren't too security conscious, but the gets and scans we got to think about. And web HDFS here, just the same way. So with that, let's think how to handle some material. Here we see, again, folks having to do maintenance on that large retriever system for plutonium. And we don't want our users to have to put on bunny suits. So with that, let's think of the properties of radioactive materials versus the properties of the data we use. Radioactive materials can be really harmful to people, and it's really frustrating too, because we don't quite know how much can cause what harm. It's a little bit stochastic, a little bit probabilistic. But they do have a very long hazard life if they're released into the environment. In case of plutonium, again, I believe it's 23,000 years before it just halves itself, and then we still have it just at half the quantity for another 23,000 years. You know, we have to think about isolating them to prevent their spread. Much like radioactive materials here, they're very, very small. So the speck of plutonium can potentially wedge itself in your body, cause you cancer. We've got to catalog and characterize these things. After a criticality incident where you have radioactive materials combining, you don't actually know what radioactive materials you have. You know, you should have some more, but which kind? And then you have to machine them. So again, it's that robotics and PPE. With data, it's harmful to people in small quantities. If you lose your birth date and in the US, your social security number or your national ID number potentially in another country, that can be harmful to you until you die. You can't really change your birthday. That hazard life is then frustratingly your lifetime, which is kind of frustrating again. And it should be isolated to prevent its spread, right? I don't want, yes, people might need to know that, but I don't want them to be sharing it with the world potentially. And it needs to be cataloged. There's a big difference between you knowing my height and my fingerprints and my birthday. But still, we need to be able to use them, and they can be used. But how do we do that with continuous automated deployment and workflow automation in Gloveboxes? And to kind of drive home the point of how long this hazard life is, some recent data breaches have been kind of scary. Probably a lot of folks, if you've had friends use Yahoo Mail in the past, get emails from what appears to be their account at random domains, and that's because of an address book hack many years ago that still people get spammed with. Similarly, the Office of Personnel Management in the US managed to lose the entire family history, career history, psychological history of all of its classified employees. This actually led to spies having to be recalled out of countries because, well, now those governments kind of knew who the spies were in their countries, as well as their entire families. So this is kind of a big concern, right? With data, we have a pretty strong requirement here. It may not last 23,000 years, but it still lasts somebody's lifetime. So how do we cause data non-proliferation? Here we see nuclear non-proliferation. Sadly, all the radioactive materials from Colorado, they were luckily packed up, cleaned up, sent off to Idaho in the US. So with that, data proliferation, we don't have to worry about terrorists the same way as the nuclear industry did, but we do still have hackers, which effectively end up being terrorists for us. Accidental loss, if you lose a radioactive sample, that's going to be bad. If you lose a USB stick full of somebody's tax data, that's also going to be very bad. In the US, we have this law called Price-Anderson Act. It means if you're a nuclear operator of a power plant, you're only liable for the first $9 billion, roughly, I think it is currently, of damages. After that, the US government's liable for it. For all of you who are working under GDPR, you understand that that kind of world doesn't exist for us anymore. In the data world, we actually have to be very careful about our loss of data, and it can be significantly impactful. Data sovereignty, similarly, we've got to make sure that we actually are processing data in the right countries and we aren't accidentally moving it to the wrong countries, and that we're bringing the computation to data. And with that, we've got to make sure to catalog and classify our data. Data swamps are not anything anyone wants to deal with, but specifically for critical data like this. There's some tools to help us. They're kind of outside the scope of the Glovebox technique, but they're worth bringing up. Lineage and masking of data. And certainly, probably some of the talks you've gone to today or yesterday, you've heard about Apache Atlas and Apache Ranger. They provide some of these techniques, which are in addition to the Glovebox techniques. So what do? Do we lock everything down? I mean, we could put a guard tower in front of our Hadoop cluster and just tell our data scientists to stay away, but that seems like kind of an awful waste of their salary. So how do we lock data down and make it a little better? First of all, we probably need perimeter controls regardless. The infrastructure of the Hadoop clusters need to be protected. And so you're still going to have IT firewalls much the same as you have today. You're still going to want to do best practices, such as encryption at rest and on the wire. You're still going to need to do authentication. And this is still much more key now, because you need to know who everyone is. So in the Hadoop world, that choice is kind of made for us. It's usually Kerberos. And we're going to want to have client location controlling usage. So now this is the huge concept that really starts to come in, is thinking of the directionality of your data. You no longer have data on an HDFS. You no longer have data on a database, and they're somehow linked. You actually have to think, this data comes from the HDFS by this user, and it goes over here. So data comes in similarly from an insecure network. Maybe I have a bunch of NiFi instances or little Internet of Things devices that are pumping data in about people's homes, and that's very sensitive. Well, it still needs to come in somehow in a secure way. Data can't come back out, and we need to allow validation of transmission from anywhere. So that's always kind of a challenge, right? I need to be able to validate the data, but I can't read the data, right? Well, let's think about that. And we want normal usage for people who need to do analytics. So an example of this technique is for a Dropbox filter for Web HDFS. Web HDFS gives us some very nice primitives for this. It gives us a very trivial way to upload data. We can see here in the curl command that it's effectively a one-liner to create a file, and just being able to create and put that data. I can download the data very trivially. That's not so great for our Dropbox, but it does make life better for data scientists potentially. And we can checksum the data, and this is a key part. If you aren't aware of it, HDFS checksums the data every time it gets uploaded. And you can always query what that checksum is, and then compute that on your local machine too. So the one nice thing is this means the data node now in the HDFS is responsible for telling me that that data was A, uploaded correctly, and B, still there correctly, without telling me what the actual data was. But this also implements a very key part here. We've got both the protobuf RPC for HDFS, and that's secured nicely by Apache Ranger today, and then the RESTful API over HTTP2, or HTTPS if you're being properly secure. That today is unfortunately not secured so that you can't pull data back out. But one really nice thing about a lot of the Hadoop daemons you may not know is most of them are based on a servlet design. So this is a Java Web Services technique where you can actually have different processors just injected in, and then you've got your final request handler. And so here we see our client curl that we saw in the last slide, talking through an HTTP server. That could be Netty, that could be Fred-ending Jetty then, which is a servlet container. And that servlet container allows us to plug in filters, and in particular, a Dropbox filter. So what does this Dropbox filter do? It takes user info in, provides the user info out, and hands it off to Web HDFS. Key part is it can also reject a transaction or reject a request. So here, it's a very simple thing to do, but now we can say, hey, I've tried to read data. I'm sorry, no, you can only put data into this system. It's a very simple concept, but it's one that I haven't seen used very much, and it's worked very well for us to try to be able to provide a directionality to our data. This is going in through HDFS 14.234 if you have any comments that you want to leave on it. And with that, let's think more about the overall Glovebox architecture. Here we can see a fellow processing a plutonium ingot in his hands through a lead-lined gloves there. And we can actually see an induction furnace, if I recall, right, on the right-hand side with all of the various glove ports necessary to move material through an actual foundry furnace that melts metal. Kind of wild to think about melting a radioactive substance, but that was how plutonium was processed. Also, similarly onto the robotics, here on the left-hand side, we can see an actual, I love the terms for these, chain veyor. There were conveyors, but they're dealing with big, heavy blocks of metal, so they're made out of chain, moving the material from one building to the other, or just even through a series of glove boxes. So with that, we need to think about the leaded pane of glass. So we need a limited RDP system, some sort of remote desktop system. Some key attributes of that are we need to think about not being able to copy data out. Copy and paste. Pasting in is great. You can paste code in, you can paste whatever you wish to do that way, but you can't copy data out back to your local client. You don't want to have file shares for that same reason. Those file shares would have to be unidirectional, only taking data from the client again. That's pretty hard to achieve, so usually just disabling it. And we need to, again, isolate per user. On that remote desktop system, I need to be very careful that data scientist on project A doesn't interfere with data scientist on project B. We also have to think about tools that that scientist might need or that user might need, because again, they aren't going to be able to pull external tools very easily into that environment. So often this means a Jupyter or Zeppelin notebook of some sort, and quite likely if they have to SSH into the cluster, an SSH client. How do people manipulate data then becomes the next question, and that's that glove port and robotics analogy. So we want to manipulate our data, but with code. And for that, we can run a compute cloud on Yarn. That's the beauty of Yarn, right? So at least we have the ability to submit jobs that run SQL through Hive. We can run Python or Scala very trivially through Spark. And now due to Yarn services, we can actually deploy an application arbitrarily. And the great thing is, because of this infrastructure, we really don't have to care about what that application is. And we'll get more to that. But we need to have still automation to ensure that things are running smoothly. So this is where usually Apache Oozie or perhaps Airflow or some other scheduling system comes in. And we want to have something so that we can routinely schedule these jobs. We can do kind of known reports. And a very key thing here is the same way that processes would be generated in a very radioactive environment, and those materials would be taken out of the facility, they might have to be decontaminated. That's much the same if we're, say, generating a user's bill. We might have all sorts of individual line items that we can't really release, but the user needs to know so they understand why they're paying us $50 at the end of the month. Similarly, we can actually run things as non-humans, so that's always nice for being able to do data exfiltration. This way, there's not actually a human in the loop saying, this data is clean. We can look at a process and say that process is repeatable and verifiable. So some key techniques for that are mentioned in now Oozie in a talk that I gave at ApacheCon 2 years ago for using the Oozie Git action. And so the really key part here that's very nice is we can now actually not have a Jenkins outside the cluster with Kerberos credentials and all sorts of ability to manipulate data in the cluster, but we can actually have Oozie inside the cluster pulling remote artifacts into that cluster and deploying them. So for example, say you have a Hive script and somebody's updated that Hive script, you can say, hey, there's an Oozie job that pulls that SCM every 5 minutes and pulls it down into the cluster for us and deploys it. Next thing we need to think through is what does our pass-through look like? In the physical world, this was negative pressure. This meant that all the air would come into a room that was radioactive. Here, we want all the data to come into our data glove box. So we only exfiltrate decontaminated data. We do that through a process of handoffs. Basically, these are not, again, firewalls as we know them in the IT world, where it's a layer 4 device, it does deep packet inspection, but has demand in the middle, everything. So, if you did any encryption, well, that was neat and all, but you need to break that somehow now. And then we also have to have policy rules, which that works great when you have 50 users and 50 files. But when you have 500 users and maybe 50,000 files, a firewall doesn't scale really well to all of those rules. And even still, they're just prohibitively expensive. Most of us probably have Hadoop clusters that are at least on 10 gigabit networks now, and that's usually like a 5 or 6 digit price tag. It's just not worth it. So how do we then fix this so that we can do this on the cluster? And that's where the technology-specific tooling really comes into its own. We've got the Dropbox Filter for Web HDFS. We have databases that can act as a pass-through, and relational databases, in particular things like MySQL, are great because you can actually individually be able to permission things such as write or read only attributes for a user. So now you do have to work with maybe a DBA who's outside of the bounds of your Glovebox, but as long as they can ensure that their access controls for your Glovebox are appropriate, they can ensure that there's only read-only access. Maybe you need to get access to host logs and things like that that are stored into the Glovebox, but you still have to look at your host map and your DNS from outside from a database. One challenge, however, HBase today has no built-in client location filtering. The HBase ACL tables, if you've ever worked with them, are just simply a user and a permission. There's no way to put a client in there. One very nice thing is Ranger can do that for the RPC side of HBase now. So we have to think about firewalls within the cluster, and this is where things start to get kind of tricky. So we don't, in the case of plutonium, they would mill it, and you'd end up with these shavings on the bottom of the Gloveboxes. And these shavings would accumulate, and after a long enough time, you'd have enough plutonium that, again, they'd spontaneously combust. Well, with our data, we don't want to do that. And you end up with shavings in your Hadoop environment as well. File systems leak in various ways. There's the obvious ones, which is maybe somebody just permissioned something wrong. And there's plenty of tools to handle proper permissioning. But now we have to think of user collaboration. What if data scientist A and data scientist B on project B both share a common project C that can use A and B's data? Well, now this is a mixing spot, and this starts to get much more difficult. Some other key parts are temporary and failed jobs. So if a Hive query fails, it will leave data often in a temporary data location. That temporary data location, however, can be introspected later, and often that's in a directory that's readable by everyone. So if the permissions on that file aren't right, I now have just some random user who can see sensitive data. Similarly, we have /temp often on an HDFS file system. That /temp is, again, just a temporary spot, but it's a temporary spot anyone can write to, and that kind of breaks this model. It is possible to operate a Hadoop cluster without a /temp directory, and I encourage folks to definitely think about how to do that. Oftentimes, some other key things are you have to override user directories and such to make sure that it points to a project-specific directory for like the Hadoop user's home directory. Local file systems, too, are just kind of a nightmare. Every Linux box has a /temp directory, a var temp, dev shared memory, all of these locations. At least the Linux file systems can be manipulated in a very clean way. Next thing we've got is there we go. Can be manipulated in a very clean way. Basically, we have to take out the trash, though. In the case of Rocky Flats, one of the challenges was they had a number of fires at the facility, which spread plutonium all over the greater Denver area, unfortunately. But with that, they had to actually ship all of the burned material that was no longer operable somewhere. Again, Idaho was the recipient, unfortunately. One of the very fascinating things here was they decided that it took too long for them to orderly unload the 55-gallon drums. And they said, you know, if we do it fast enough, they don't have to wear protective suits. So instead, they just made these 50, it looks like shipping container dump trucks, and just told the guy, yep, you just got to dump it as quick as possible. One thing that I thoroughly loved, this picture is actually from an Idaho Labs report recently, where they said Rocky Flats was a great cleanup. All of the waste is now in Idaho, and they've actually been having to try to figure out what the waste actually is. Luckily, with our Linux systems, hopefully it doesn't ever get that bad. We can instead have things that make private temporary directories or private home directories. So with this, we want to provide isolation. And there's the pluggable authentication module stack in Linux, PAM, as it's often known. And it provides a very nice feature where we can use Linux namespaces. Now, Linux namespaces you may not know by name, but Docker uses them. That is indeed how Docker, for example, has processes that run in its own environment and doesn't see the broader systems processes. That's how Docker can have a user account that doesn't actually exist on your broader machine. Here, we're just using simply the namespace construct, not all the other fanciness. And we will set it up so that when a user logs in, they exec a couple commands that creates a directory for them. So here we can kind of see on the left-hand side what the broader machine might look like for, say, the root user. They would see the slash of the file system. They would see /temp, which would be the normal /temp. But then they would see this interesting directory, and you can call it whatever you want, but the CS term for it is polyinstantiation. We're instantiating things multiple times here, so everyone has their own individual temporary directory. So root, or somebody who's permissioned properly, can see this. Then we might similarly have home, but again, this home might be different. So now we log in as user Clay, and we see instead that temp's there, but it's no longer inode 100. The file system actually points temp somewhere else. And now it's pointing to the same location that temp_clay was in the polyinstantiation directory. So one of the beautiful things here is every user now has their own version of temp and doesn't see anything shared with anyone else. An example of how we integrated this with our Chef environment can be found on github.com/Bloomberg. So One of the key things, though, is we need to keep the pipes flowing. Luckily, our pipes don't contain mystery liquid. Never could figure out what this pipe contained, but it ran around the whole complex. It was a really big pipe. But Yarn, we need to keep the bits flowing. And with that, one of the key things, as I mentioned, is we have to make sure that network services run by one user can't be talked to by another user. And one of the challenges here is, how do we achieve that? Well, Linux, again, comes to our rescue. Again, in the Linux kernel, there's something called network classifiers, or network classes. The network classes give us a very nice construct where we can say all of user A's processes run in one class, all of user B's processes run in another class, and even better, IP tables, or the Linux firewall, can let me filter on those classes. So now I can say user A can talk to the two databases that user A is permissioned for. Maybe user A pulls in data or writes data back out in an appropriate manner, but user B certainly shouldn't talk to those databases, and we can control that at the Linux firewall layer. One of the key things to think about, though, is I also have to make sure those firewall rules allow me to talk to all of the in-cluster services. So this is HDFS and Yarn, Zookeeper, HBase, et cetera. So as long as you write your firewall rules so that you have kind of a generic cluster specification, and then you can just put in specific exceptions for every user, well, this means all of your data scientists who probably ought not to have explicit external access on the cluster can be isolated down, and whenever they spin up a container on the machine, they're unable to talk to the broader world. But we don't have to buy one of those really expensive physical firewalls that doesn't have the configurability we need. So one of the key things is firewalls are important. When they failed at Rocky Flats, it usually involved a very large fire. I believe the right-hand side, the 1970 incident, was the most expensive industrial accident in the US at the time. The one on the left, they didn't bother to tell anyone about, but it spewed radioactive smoke was the expectation for at least a couple hours. So one of the key things, data Gloveboxes involve here a leaded pane of glass, some way to observe your environment. So that's kind of the remote desktop without a copy. You've got glove ports, some way to manipulate your data. You want it to be manipulatable, and kind of a key thing to think about is that at an arm's length. You want everything that actually is kind of a sensitive function to be removed from a human. It's a distant process that they can't directly influence. But everything that's central to their experience, doing the actual data analysis and stuff, they've got to have hands on. Thus, we need robotics. That's kind of the broader workflow management. Some people, when I talk to them about their Hadoop clusters, they're like, oh, we use cron. I don't know, there's Bob. He just comes in every day and he runs a process. And that certainly can't work in this environment terribly well. And we need the pass-throughs, some sort of negative pressure to keep the bits flowing, and then firewalls to ensure that users and workflows are isolated. Otherwise, cleanup's messy. So with that, this was, I think, again, yeah, the 1969 fire that we're cleaning up. So thank you. We've got about 8 minutes for questions. And I think if anyone has a question, they've got 2 mics that they'll want you to use. But cool. You guys are letting me off easy. Thank you. Yes.
I might have a question on the MySQL. I might have misunderstood something, sure. But yeah. So maybe for clarification, you were using the MySQL database as a pass-through, right?
Correct. So,
right.
Yeah, you can make the MySQL so that it is permissive to only allow reads or writes. So in the case of MySQL, that might be hosted in a Glovebox. You might set up all the users to only have write access if they're an external user. If it's hosted outside the Glovebox, all of the data Glovebox users might have read-only access so that they can't exfiltrate data unexpectedly. So it's a pass-through, much the same as in the Gloveboxes, where ideally things can't flow uncontrolled through there.
Fair enough, yeah. But your experience, according to your experience, it is scalable enough, you mean, for the amounts of data you want to pass through?
So I wouldn't recommend using MySQL if you had to exfiltrate a terabyte of data, but it's just one of the many ways. So relational data, quite often we'll find use cases with the data science world where they need mapping tables. And the frustrating thing about these mapping tables is they might change really frequently, but they're unfortunately really small. Kind of unfortunately, because that means that no one really wants to deal with them. They're not a sexy data set because, well, it's only a couple hundred kilobytes. Yes, but without it, I don't know anything in this terabyte data set. OK, well, we need to find some way to get that to you.
The DBA, or that MySQL, that's important person, I guess.
Yeah, so one of the key things to think about, and this is really organizational politics. Certainly I've worked in some companies where things are very siloed, and that might be very hard to build such an environment. Bloomberg's luckily a really collaborative environment where you can actually make sure that, hey, I need these policies, and rigorously, if you ever allow a write policy from this network, I need you to be able to make sure that you notify me first, or whoever is the data controller, if you will, for that environment. So. Do you have a question?
I was going to ask, well, I'm not really sure if you're allowed to say this kind of stuff, but is this something where there are actual prod users, customers?
So the question is, do we use this in a production manner? And indeed, we do. I can't tell you what use cases are on the clusters, but yeah, we've got over 100 users permissioned for this environment, coming from more than 20 projects. So, and each of those 20 projects ingests at least one data set, some I think a couple hundred. So, yeah. One key thing is so a lot of the impetus for this has been trying to make sure the core Hadoop processes support this, kind of to the point of the database administrator being a very key part. We really want to try to set up axioms where it's as simple as possible to control this environment. So instead of having a very complex policy, we try to go as simple as possible. So like the data Dropbox technique where we have rules that can specify who can actually exfiltrate a file, what their username is, what the host that they can come from. If we keep that as simple as possible, that kind of helps on inspection, where a human can quickly look at it, and you don't end up having to have a rules solver that tells you like, oh, hey, you've got a hole in your security here. So that's been kind of a key driver for this. So.
One more. You indicated you had IP tables running on each data node.
Correct.
Yeah, can you elaborate on what policies you're running there? Because I believe there's going to be a lot of ports with high numbers that simply needs to be open.
Yeah, so it depends. One of the key parts here is the fact that we've got the IP classification. So I don't actually have to care about the port. Like Spark is a great example. It starts all sorts of ephemeral nodes. Ports are all over the place. Luckily, I don't have to care. I can just say that network class is open, and I can say that network class is open in various ways to talk to say, the Yarn resource manager and things like that. So now there is some challenge that you have to definitely make sure things line up on the fellow executor nodes, and so that starts to become kind of a challenge.
Okay, so what you really want to prevent happening here is any of those data nodes talking to the wrong web service or any other perimeter things.
Yeah, so you can use it from a user isolation perspective on the cluster too. That often, when users start doing that, they should realize they're doing something malicious. Like, why am I having to work so hard to figure out where Joe's running his process? And, I mean, he's running it on 100 machines. Gosh, it's always difficult, and it keeps changing every 30 seconds. Wait a second, this is a lot of work. I might be doing something wrong. So yeah, you can potentially outrun it. But with regards to the external resources, they're at least much more fixed and much less dynamic usually. So you can kind of choose your sensitivity there. Some tools also that can help with that are the BGP. Thank you, Calico. So, sorry, SalWorks on my team. Calico, though, is a tool that you'll find folks will use in the Kubernetes world, and it actually gives you a uniform policy deployment process, so that helps out too. So. Cool. Well, thank you, guys. Thank you, everyone. Yeah.